Hello everyone, welcome back to Physics 11. Today we'll be looking at gravitational field strength. So if you remember before the break I mentioned that the planet Earth is not a perfect sphere and it's slightly squished at the north and south poles, so it bulges out at the equator. So we're going to be looking at how this affects the basically force of gravity or the gravitational field strength around the planet Earth. So first, to help explain how two bodies can experience the force of gravity without actually being in contact, we have this definition that we call gravitational field strength. And this also, the same type of concept applies to other types of forces which are not the objects don't have to be in contact to actually experience the force. So other cases is going to be electromagnetic forces, which you will learn about in grade 12 physics. So in order to explain this, we use the concept of vector fields or just fields. And again, once you do some calculus later in the future, you will see this in more details. So fields are spheres of influence. So basically they emanate from a body or a particle in a spherical fashion. These are invisible, intangible, you can't touch them. They are simply to demonstrate how strong a characteristic at a certain distance away from the body is. So how strong that force of attraction or maybe repulsion is a certain distance away. Now this will depend on couple of things. So here's an example that we can think of when we think about field strength. So let's say you have a fire, and depending how close you are to the campfire, you may feel the heat more or less. So for example, if you're closer, the closer you get to the fire, the stronger the field becomes. The further away from the fire you are, the weaker the field is. Now also this will apply to how big the fire is, right? So the bigger the fire, the stronger the field is going to be. So same idea with particles or objects or bodies. The bigger the mass the object has, the stronger the gravitational field is going to be. So same idea here with the fire. So the larger the fire, again, you can be further away and still notice its field. So now let's take a look at how the gravitational field is defined. Now here we have our g, which is normally we use as the acceleration due to gravity. But in this case, even though this equation is derived from force of gravity equals m times g, the context of this is slightly different. So the definition for the gravitational field strength, if you look at the full equation from the universal gravitational force, this is going to be the full equation with the capital G and the mass of the body you're trying to figure out the field strength that's acting on it. So the units that we're going to use for G are going to be newtons per kilogram. Okay, so normally you use this, we treat it as a acceleration meters per second squared. And if you look at these two units, they're actually fundamentally they're equivalent, they're the same, because if you break down newtons and you simplify it with kilograms, you will end up with meters per second squared. So here it's just about context. It's not so much about the difference in units, but G has two meanings. You can think of it as just acceleration due to gravity at a point, but when we talk about field strength, this acceleration can change depending where you are on the surface of the planet or how far away from the planet you are. In that context, if we consider all the possible points around, let's say if we're talking about Earth, the sphere of influence, we're going to talk about the field strength. So in that case, we're talking about G as the gravitational field strength. So we're going to use the units newtons per kilogram. So let's take a look at some examples here. So the first example, it says again, Earth is not actually a perfect sphere. It's just like a spinning basketball that's oblate spheroid. So basically, it's kind of squished at the south and north pole, and the equator kind of bulges out. So the question says calculate the acceleration due to gravity if the radius at the North Pole is 6.370 times 10 to positive 6 meters. So again, all we have to do here is take our equation for the gravitational field strength, which is again defined as our lowercase g in this case. Again, this is also a vector. So capital G times the mass over r squared, right? So we're going to plug in the value for the capital G, which is the universal gravitational constant of 6.67 times 10 to negative 11, so again, very small number, times the mass, which in this case is the mass of the planet Earth. So we're talking about what's the field strength, so we're talking about the object that's causing this field strength. So the mass of Earth is 5.98 times 10 to the 24th kilograms. And the radius is going to be 6.370. And don't forget to square this. Okay. All right, so our answer should be close to 9.8. In this case, we get 9.83. Notice the units, I'm going to use newtons per kilogram. And again, fundamentally, this is equivalent to meters per second squared, but because we're talking about field strength, I'm going to use these units and not meters per second squared. So I have the ability to differentiate between the two concepts, okay? So it's not just acceleration we're looking at the field strength. So at this point on the planet Earth, the field strength is going to be 9.83 newtons per kilogram. Now, part B says, what's the field strength at the equator? So again, at the equator, the radius is going to be just slightly bigger because, again, it's squished at the equator. So let's take a look at part B. So again, the only difference here is the radius is a little bigger, but the process is going to be exactly the same. We're going to take our equation for our gravitational field strength. Plug in the value for the universal constant, the mass of the Earth, and divided by the radius at the equator, which is going to be 6.386 times 10 to 6 squared. And this is, again, one of the reasons why most rockets are launched from the equator, because the gravitational field strength is slightly lower there. But this is a big difference if you had to launch a huge rocket into space, because it saves a lot of fuel and they can actually launch bigger payload into the space. So as you can see, before we got 9.83 in part A, here at the equator we get 9.78. So that's very small difference. If you were just to round to one decimal, you're going to end up with 9.8, right? That's why we use 9.8 as our average value whenever you do any calculations with acceleration due to gravity. But in reality, there are some small differences. So that's why we use, again, we launch rockets from the equator because of that slightly lower field strength at that point. So we can save some fuel, and it basically becomes a lot cheaper to launch rockets from there than it would be from anywhere else on the planet. Okay. So let's take a look at another example. So in this case, we're on the moon. And the moon is 385,000 kilometers away from the Earth's surface. So what is the Earth's gravitational field strength at this distance? So again, we're talking about the gravitational field strength of the Earth. So Earth is going to be the mass that we're going to use in our calculation. So this is going to be our m value in our equation. Now again, the m value of Earth is the one we used in the previous question, which is 5.98 times 10 to the 24th kilograms. Again, that's in your formula sheet for reference. Now, the one thing we had to be careful of are the units. So we had to be vigilant of that and make sure you convert them before you plug them in and you do your calculations. So let's see what we do here. So we have our equation G equals capital G times the mass of the Earth over the radius squared. Let's take the value for G, 6.67 times negative 11, 10 to negative 11, and then multiply by the mass of the Earth, which again is 5.98, 24 kilograms. Okay. If you converted kilometers to meters, you just had to add 3 zeros here. So this is basically 385 million meters. Or if you were converted to scientific notation, count the number of zeros, which end up being 678. So 3.85 times 10 to the positive 8 meters. That's the number we're actually going to plug in for our R in our equation here. So we're going to plug in 3.85 times 10 to the 8, and don't forget to square it. And then we will get our field strength, this distance away from the Earth. So we get 0.0027 newtons per kilogram. Okay? So this is kind of a basically continuity to the previous video that we looked at the universal gravitational law. And this is just an application of it because we took that equation, we solved it for the little g, which again comes from the equations that we saw before the break, right? Now, actually, since I had the space here, let me do quick reminders. So remember, we did this, and then we did this, so let's call this M1 here. And again, we said that, well, these two are exactly the same. So another way you can derive this equation that we're using here, because Fg and Fg are force due to gravity, we can equate both of these equations. So we get M1 times G equal to G M1 M2 over R squared. And as you can see, we have M1 in both of these. So the M1 would reduce away, and we're left with the equation that we have. G equals, lowercase g equals to capital G times M over R squared, right? So that's how you can derive this equation in case you forget. Okay, now there's no questions that follow just this section. So the next section is on satellites, which is going to be in the next video. But if you have any questions from the next worksheet, which is going to be 5.2, make sure you post them in the comments so I know that you're doing the questions first of all, and also I can go over them later on. Okay, so the next video is going to be on satellites.